Hello and welcome everybody. This is Tobias König from Paris. Uh, First off, thank you very much for your interest in my talk. And big thank you also, of course, to Hojo Lee for organizing this wonderful series of conferences. I will be speaking in my talk about a recent preprint of mine together with Paul Laurent from Paris, entitled Constant Q-curvature Metrics with a Singularity. So here is the basic object that this talk will be about, namely the higher order Liouville's equation that you can see written here. Note that we treat any space dimension n greater or equal to, and the order of derivatives is exactly equal to the space dimension. So in particular, when n is odd, we have a pseudo differential operator here. And so the main feature of the equation that we're considering really for the purposes of this talk and for our result is that we are allowing the solution U to have a singularity of the simplest kind possible, namely in zero. Moreover, we assume that this finite integral condition is satisfied, and I actually will denote by capital lambda the value of this integral, which I will refer to as the mass of the solution. And I'm introducing this right now because this will be a recurrent topic in the talk, what values this capital lambda can or must take. We will be interested in getting a picture as complete as possible of the structure of solutions to this equation, including the singularity. To start getting a picture of the structure of solutions, one has to notice, of course, the one family of explicit solutions that exists. These may be referred to as standard solutions, or sometimes they're called spherical solutions in the literature, and up to translations and dilations, which keep invariant the set of solutions due to the conformal invariance of the equation. The standard solution to the Liouville equation in any dimension is this here. These are functions that are probably rather well known to many of you because they are nothing but the well-known bubble functions that ubiquitously appear as optimizers of Sobolev inequalities and related inequalities and the corresponding partial differential equation, and which always have the canonical form 1 over 1 plus x squared to some power. And here, since we're in so to say the limit case of a Sobolev inequality, instead of a power, we're taking the ln, so to say the 0th power of this 1 over 1 plus x squared. We can note right away that all these solutions and all their translates and dilations have the same mass, which does not change under dilations, which is a number that will be referred to as lambda 1. So to say the standard mass. And finally, to conclude this very introductory slide, to make back the link to the title of my talk, as well as from analysis back, if you want, to differential geometry, then in the language of Riemannian geometry, any solution U to the equation that we saw gives rise to a metric of constant Q curvature by this conformal change of metric starting from the standard Euclidean metric on Rn or on Rn without 0, if you will. So this also partly explains the term spherical solutions that I mentioned for the family of functions U0, because this U0 is precisely obtained by pulling back a standard solution on Sn. So let us have a quick look at the outline of this talk. There will be essentially 2 parts, and then a brief summary, and we'll repeat some open questions. The first part will be a continuation of the introduction that we just started. So first of all, I wanna give you an overview of the as I said, the structure of solutions to Liouville's equation, which it is, I think, very instructive to compare also quickly to those of the very related Yamabe's equation. And after these preliminaries, after having, so to say, set the perspective, I will be able to state our main result, which precisely gives such a solution structure in some detail. It comes in two forms. On the one hand, there is a classification result saying that all solutions must obey to some common properties, can be parameterized by simple objects, namely polynomials and real numbers, in a suitable way. On the other hand, there is an existence result that guarantees us that the classification result that we've just seen is essentially optimal. That is, given such parameters, polynomials, and real numbers, as I just saw, we will prove that there is a, and we do this in the radial setting only, that there is a radial solution obeying this. I also point out the second part of this line, that is without mass constraint. In fact, it will be of major interest to be able to prescribe this mass lambda that I just emphasized on the last slide freely, especially in comparison with previous results. The second part of my talk will then be devoted to giving some elements of the proof of this main result. A slightly bigger emphasis will be put on the existence argument, because the classification argument follows mostly some arguments that are already established in similar cases in the literature. We only pay attention to adapting these well to our settings. In the existence argument, we differ from many related works. In particular, we rely on a new kind of fractional weighted Moser-Trudinger inequalities that give us our result in a variational way. You will see in the second part what all this means in detail. So let us get started right away. And to get started slowly, let us have a look at the very classical case of Liouville's equation, which is, of course, the case n equals 2, in which case we only have a second order equation involving the Laplacian on the left-hand side. Also in geometric terms, this has a classical meaning. There is no need to speak of Q-curvature in that case. In that case, we're back at really constant Gauss curvature, which is induced by solutions U to the two-dimensional Liouville's equation. So I repeat that there is this one parameter or a two parameter family of solutions that we've already seen. And the classification result that has been established by Chen and Li in 1991 using the method of moving planes really says that these standard solutions in dimension 2 are all the solutions. So this is, of course, a very nice classification result, because this means one knows all the solutions explicitly. An interesting parenthesis to make here is that in a paper that came slightly after by Chow and Wan, it was observed that this classification result could actually be easily deduced from the complex analytic classification of solutions that already Liouville gave. So he classified all the solutions to the equation just without the finite energy condition, and then Chow and Wan realized that among the solutions found by Liouville, the only solutions satisfying the finite energy condition in addition could be the spherical solutions that Chen and Li found. And to do this, you really need 1 or 2 pages of additional complex analysis. So this is really an interesting alternative argument. Things are similar when one turns to singular solutions. Of course, one then keeps all the entire solutions, but gets an additional degree of freedom. And this additional degree of freedom is reflected in the presence of this alpha. So again, one has an explicit family of solution depending on parameters. And since we want to keep track of the mass of solutions, we realize that by being able to introduce this alpha, we can multiply the mass of the standard solution exactly by alpha. In other words, we can achieve all possible positive masses. I would like now to digress slightly and to discuss a bit the very related equation, which goes by the name of Yamabe's equation in some parts, especially the differential geometric parts of the literature, which I understand as this equation here. So this is really the higher the appropriate variant of Liouville's equation in higher dimensions. By higher dimension, I mean higher than the order of derivative, which is 2m, and if the dimension is strictly greater than 2m, we can write this equation with the critical Sobolev exponent on this side. I would like to talk about this because it really the structure of solutions, as we will see, really contrasts remarkably with that of Liouville's equation, and also because I personally, in my analytic background, I come very much from this equation. Similarly to Liouville's equation, the Yamabe equation has a geometric meaning. It's related to finding metrics of constant scalar curvature on some manifold. Then the classification results that I want to present you quickly read as follows. So notice that they are very reminiscent to what we've seen on the last slide, namely every entire solution is a bubble function. And this now I emphasize for every order of derivative and every appropriate dimension n. And that every singular solution is still can still be parametrized by an additional parameter epsilon, which I call here epsilon, which is not explicit anymore, but still tame, so to say, and does not increase in complexity as the dimension increases, for example. These results are, of course, classical for m equals 1, when we again have a second order elliptic equation here, in which case they are due to Caffarelli, Giederson, Sprague, and Chain, respectively. And in the biharmonic case, the entire solutions were classified by Lin, and for even higher orders by Wei and Su shortly afterwards. For the singular solutions, the classification is much harder to achieve. The radial symmetry statement was done by Lin in '98, and the classification result, which for the moment is really only known besides m equals 1 for the biharmonic case and m equals 2, was a paper of mine with my PhD advisor, Rupert Frank, in 2019. So to come back to, let us now come back to Liouville's equation and look at what entire solutions behave like in higher dimensions. So the main point to take away from this slide before we look at the numerous details that are written here is that the behavior is very different in the sense that the further the dimension increases, and here the dimension and the order of differentiability are coupled, so we have only one parameter n. The higher this n increases, the more complex the solution structure becomes, and other solutions than the bubble functions start arising and not only arising once, but there are really several steps of complexity that are being climbed. So let's have a look at what this says. On the one hand, we do still have a classification result that is, however, weaker. Namely, it says that if U is an entire solution, so we're only speaking about entire solutions for the moment. If U is such an entire solution, then there is it behaves at infinity like an upper bounded polynomial p, And then there is a logarithmic divergence term, which is whose coefficient is given by the mass. And then if some additional constraints are satisfied, then U really has to be a standard solution, but in general, it does not have to. Note also that that the mass is not fixed here, while in 2 dimensions for entire solutions, the mass had to be equal to the standard one. And then conversely to this, there are existence results that tell us that this classification is really optimal, namely, given any such polynomial with the additional assumption that goes to -infinity, and given any mass that is admissible in the sense of the above results, then there really is a solution that satisfies the prescribed asymptotic behavior given in the classification result. So things get even worse, because if n is greater than 5, as has been proved by Haider and Martinazzi, then we lose any bound on the mass up to adapting the asymptotic polynomial. That is, up to, in this expression, up to prescribing C1 and C2, that is fixing the polynomial. I can have a solution of this asymptotic behavior that has any positive mass without this upper bound lambda1 that was present before. So I repeat, in conclusion, solutions increase in complexity as the dimension increases in Liouville's equation, very contrarily to what was the case for Yamabe's equation that we've seen before. So after all these preparations, in the hope that I haven't bored you too much, I'm now in the position to announce meaningfully our main result, which carries over the classification and the existence result that we've just seen for general dimensions to the singular case. That is, we're considering the same equation. Now with a singularity in 0 allowed, and we still have a look at the behavior of this mass parameter lambda. And then our results reads very much as those from the last slide once again, namely that at 0 and now as well at infinity, sorry, and as well at 0, U behaves like a polynomial plus a logarithmic divergence term whose parameter is once again in relation with the mass at infinity and given by another independent real number beta at 0. Notice also that in 0 we have Q, the polynomial behavior really reads Q of 1 over x, so to say, of the inversion. So this is a very symmetric statement that is of course consistent with the inversion invariance of the equation, but inversion invariance of the equation is, as we will get a glimpse of it at least when we talk about the proof, is not enough to simply deduce this from the results that we've seen before on the entire solutions. Simply because we cannot turn a singular solution by inversion into a regular solution. In general, also after inversion, I will create another singularity in 0. And then secondly, we get the converse existence result telling us once again that our classification is optimal. And I point out that we're only able to do this in the radial case for reasons that will become clear afterwards, because the Moser-Trudinger inequality we get really only holds true in the radial case. What it says is then much like before, but it's really in the context of radial solutions is really optimal. Namely, it tells us that we can prescribe everything. We can at the same time we can prescribe the mass parameter. We can prescribe this additional log parameter beta, and we can prescribe the radial polynomials p and q at the same time under the only condition that they tend to -infinity as before. with all these things prescribed, we are still able to find a solution U to the equation, and that has the same asymptotic behavior as given in the classification result above. So to finish this introductory part, let me quickly compare our main result with some previous results in the literature, which are all quite recent because the study of this singular form of the higher order Liouville's equation has really only been taken up quite recently. An important paper in this regard, and also a great source of inspiration for us, is the paper by Haider, Mancini, and Martinazzi from 2018, who study the following special form of the singular Liouville equation. So unlike what we've written down before, they don't consider a general singularity in zero, but rather they fix the singularity to be of Dirac type in the origin with a certain strength parameter alpha. The reason why I'm choosing this funny normalization here is that because the log precisely yields a delta plus this factor when the Laplace n half is applied to it, then prescribing this is nothing but solving the general singular equation, but under the additional assumption that the asymptotic behavior of U in zero is alpha times log x to leading order. And under this assumption, they get, so to say, in that paper, the special version of our classification result pertaining to this special case. If you recall, that in general we have a polynomial asymptotic behavior in zero, then their asymptotics is exactly the same thing at infinity, and at zero it is already prescribed by assumption. In particular, this polynomial Q in zero is identically equal to zero. Another interesting feature of their result is that at least for dimensions 3 and 4, and for higher dimensions this is left open, and for radial solutions, there is, at fixed alpha, there is an upper bound on the mass that can be attained. This follows from some Pohozaev type identity. And now, in the light of this, our result is remarkable in the sense that it tells us that when we give even more freedom in zero, that is, if we drop this assumption on the delta singularity, and if we really allow a general singularity in zero, then even at fixed logarithmic term alpha, the mass can be arbitrary. This is, remember, this is what our existence result said. At the condition of course, to be consistent with Haider, Mancini, and Martinazzi's result, at the condition of having a non-trivial polynomial behavior Q in zero. For completeness, I want to mention two other works that are that pertain to the special case n equals 4. That is the biharmonic case with Laplacian squared, where the papers by Fang and Ma on the one hand, and Ahmedou, Wu, and Zhang on the other hand, give slightly more complete results, also applying different methods, which I don't have time to discuss in detail here. So they get different results also, and carry this also over to some manifold context. Still in these papers, the assumption on the logarithmic behavior on in zero or in the singularity is kept corresponding to the assumption of such a delta singularity. So it is really in our work, it's really the first instance, to the best of our knowledge, where this a general case of arbitrary singularity in zero is considered, which is certainly of interest.